So, firstly, I want to clarify my affiliation. So, I was at PI long ago, but then I did my first postdoc in Gdansk, and now I'm between moving from Gdansk to Naples. So, this is where I'm starting my second postdoc. And I want to talk about research that started during my PhD and how it's ongoing. And there are some really nice open questions that I want to talk about. And usually we get stuck at some point of understanding the Causaloid framework. So I've tried to have a version that is something we can all follow to just understand the main broad ideas that are going into this research, let's say. So let's see. So some background on the Causaloid framework. It's a framework introduced by Lucien Hardy at Perimeter in an attempt to go towards quantum gravity from a perspective of taking general relativity and quantum theory as two pillars at an equal footing and trying to marry the radical aspects of each theory together. Now, the Causaloid framework is not a theory, it's a framework to accommodate a landscape of theories that should be compatible with dynamic causal structure and probabilisticness, and even some versions of them together, which is known as indefinite causal structures nowadays. And before we go into all the details, this is the picture I'm going to end with, and I would like to also begin with it, which is where all of this has led to. So using the Causaloid framework has helped classifying some theories. So there is some hierarchy known as Sorkin's hierarchy, which relates the number of real parameters you need to describe some state with respect to the number of real parameters, the number of perfectly distinguishable states you can have of that system. And this is given by a parameter R, which you can plot on a graph, which distinguishes classical probability theory and quantum theory, right? What we do is we introduced another hierarchy, which we call lambda OD sufficiency, and we will show how both of these hierarchies work within the Causaloid framework. But the thing that we learned by studying this hierarchy is that a class of generalized probability theories called the duotensors, as well as bipartite process matrices, fall in the same rung of this hierarchy, which is kind of the upshot of this talk, because what this might help us with is kind of a program for reconstruction reconstruction for quantum gravity akin to the reconstruction program for quantum theory from physical principles. And this is something that we are still figuring out if this hierarchy can help give us one of the physical principles towards that. Okay. So what is the Causaloid framework in a nutshell? It's a framework where we are centering operational methodology. So what we have is that we assume something very big. We assume that we have all the logical possible data that you can have in whatever you're studying, let's say the universe, but maybe let's start with something smaller, which might be a smaller region, your laboratory, for example. And on this data is given to a person in a room through these cards, which have some information on them. They have information of what location at which this experiment was conducted, what actions were done, and what observations were found. And now this person has all these cards, and they go through organizing these cards, and they find correlations within it, because any physical theory will correlate this data. And then the task is to compress this data such that you end up with the fewest number of cards, such that you can go back to the full set of cards if need be. And what we're really interested in are conditional probabilities of what happened, what outcome you found in some region, given what actions were done in that region, and actions and observations in any other region. So these are the things we want to be able to calculate, these probabilities. And at the level of operational methodology, we say this is akin to the theory itself at the level of, without going into ontology, let's say. And of course, we need to be able to go to these probabilities from some notion of state and measurement. But one of the motivations for the Causaloid framework is to not have an assumption on the order of causal structure, and yet the notion of state and measurement itself have a notion of causal structure embedded in it, where we think of the state being prepared and the measurement that happens after a state is prepared. So here we try to generalize these notions. So here you have some probability. This is a number, and it's indexed by all these wires corresponding to the different regions, and the alphas correspond to the index on these wires. And we want to understand this probability in terms of some generalized bond rule, where the generalized measurement is essentially anything you can do in this region that you're considering, and the state is everything that's prepared and you don't have control over within this region. So these equations can look differently depending on which wires are on your measurement and state, for example. And then, of course, this is now just organizing the cards that one started with, and we want to compress them. And there are 3 levels of compression in the Causaloid framework. So let's talk about the first 2. So the first one has to do with tomography. That's why we call it tomographic compression. And essentially what you do is you take each region and so the lambda box represents a matrix, a very rectangular matrix at that, which takes you from some index alpha to a fiducial set indexed by L1 for the region 1, and so on for each region. And what you might want to think of is maybe an example will help. You can think of a Stern-Gerlach experiment, and you can say that, well, alphas correspond to all the settings, and all the settings are all the angles, and therefore the list of alpha is quite big. But we know that to do tomography, we don't have to know the outcomes for each theta. We can go to a fiducial set, and this is what this set looks like here. But now, once you do tomographic compression on each region, each elementary region, there's some more compression that can happen, which comes from causality. So when you compose these regions together, there might be some causal relations between them that reduce the description that you need to describe the total state compared to the, let's say, the individual states. And this we see maybe from an example of like composing quantum channels. So if you compose 2 CPTP maps, the resulting CPTP map will be described with lesser elements. On the other hand, if you have 2 channels just composed parallelly, then the number of parameters to describe this composed CPTP map is also equal to just the multiplication of the original 2, which means that compositional compression is non-trivial when you have some causal adjacency between these regions. And then one can write down the causaloid itself by writing down the tomographic compression lambda matrices and the compositional compression lambda matrices for all regions. And this itself is able to give you back all the conditional probabilities for all alphas. So we call this the causaloid, which is akin to the theory, describing the theory itself at the operational level. And you can use this causaloid to define a causally neutral product. So the causaloid product, which you can reduce to the tensor product or composition in quantum theory, but more in GPTs, this would just be parallel composition, sequential composition, and so on. And if you have indefinite causal structure, it might be something in between. So let's go to the third level of compression, which we didn't touch on, which is called meta compression, because what we do is we compress the causaloid itself. So the causaloid was this tomographically compression matrices, these lambda matrices, the compositional compression matrices, which I've listed out in terms of like the number of wires that are going in and out. So 2 region, 3 region, and so on. And as long as you can compress the description of the causaloid itself, given some rules, you have some meta compression. And here we define a hierarchy by cutting this off at D regions. And as long as you provide the rules to get back lambda ON, where n is greater than D, then you can say you have some meta compression with your causaloid being described by a smaller list. And we call this rung of the hierarchy lambda OD. And of course, lambda O1 is, so if we only had everything explained through tomographic compression, it's not a very interesting level because we don't have any causal connections between regions. So this is something that is kind of trivial. So the next, the non-trivial layer would be lambda O2. So we go to lambda O2 and try to study this. So for the purposes of this talk, this is sufficient to consider 3 regions only. So here we had n and d. So if you set n to 3 and d to 2, this is what we're trying to show here explicitly. And here then we can just list the causaloid explicitly in terms of tomographic compression, compositional compression of 2 regions, and compositional compression of 3 regions. And you can define diagrammatically like the equation that must be satisfied if you want to describe this matrix in terms of these other 6 ones. And you can also, let's assume some causal structure between these regions. You don't have to do this, but this will come handy. So we're doing this here, where we say that region 1 and 2 are causally adjacent and region 2 and 3 are causally adjacent, but 1 and 3 are not. Then the above equation reduces from the previous slide, reduces to this equation, where we can characterize the lambda matrices. And we can also, the indices belong to these omega sets, and we can also describe how these sets are related. And now we're going to use this equation again and again. So we're going to okay, before we go into this, just to say that we assume some specific causal adjacency relations between these 3, but you can do it more generally. It's completely allowed, but we did this particular case for some utility that you'll see now. So now we try to apply the Causaloid framework on the duotensors and the bipartite process matrices one by one, just to show the conclusion that I started with, that we find it on a particular rung of the hierarchy. So let's start with this equation, the Causaloid equation, and we try to massage the duotensor, which is a framework for GPTs that have a circuit structure. So they're a family of theories, and you can massage this such that you can now start trying to identify these lambda matrices in terms of the objects of this circuit diagram. And once you do this, you might realize, if you stare at it for long enough, that the lambda matrices can be understood in terms of these duotensor objects, which is beyond the purview of this talk, but I'm happy to talk more about it. But what we do is we show that you can actually describe any lambda O3 matrix in terms of the tomographic compression and compositional compression of 2 regions. And therefore, we can conclude that the duotensors fall on the second rung of the hierarchy we introduced. But the duotensors are a kind of post-quantum theory, but they don't have indefinite causality. So the next question was, we know some frameworks such as the bipartite process matrices, which have post-quantumness, and how they would look like within this framework. And now again, it's the same equation we started with regions 1 and 2 causally adjacent and regions 2 and 3 causally adjacent. And we want to check if these equations hold for the bipartite process matrices, where we identify the bipartite process matrix as region 2 and the 2 CPTP maps A and B with region 1 and 3. And you can do at the level of sets, you can check that this equation holds. And then once you do this, you can write down the elements of your process matrix calculations and check if this relation holds. And since it does, we can conclude that the bipartite process matrix is something that these things that violate causal inequalities, have indefinite causality, also fall on the second rung of the hierarchy. So we have two different, very post-quantum directions that fall in the same rung of this picture, which is in terms of this hierarchy that we talked about. And going forward, I would like to figure out what this means, if it can help us shed some light on constraining this landscape for quantum gravity. And one way to do this, one open question that's on my mind, is to see if an operational version of GR could be seen within the Causaloid framework through this lens, and where it would fall on this table, to shed more light going forward. Yeah. So I would like to stop there with this slide depicted. Yeah. And thanks for having me in this session, Rick.
Amazing. Thank you so much for joining, Nitica. About the affiliation, let me just tell you, because you're a member of the ISRQI, I don't have any control over the affiliation there. It's associated with your ISRQI account. So you have to change it in your account there if you want to see it changed. Yes.
Okay. Okay, yeah. Thank you so much. Yeah.
No worries. I'm gonna send you a short message about how to actually change it, but that's yeah. Thank you so much for your talk.